Hey guys, welcome. Yeah, so if you haven't watched the introduction video to complex numbers and polar coordinates, then you should. I'll link it below this video. But yeah, with that or your own other ideas about the basics, in this video, I'm gonna teach you how to multiply two complex numbers and polar coordinates. So first, we're gonna come up with the general formula. So we're gonna derive the formula for multiplying two complex numbers and polar coordinates, and then we're going to offer an example. Yeah, all right, so let's get on with it. From the intro video on complex numbers and polar coordinates, we know that we can write a complex number and polar coordinates as this here, r cosine theta plus I times r sine theta. Now, so then it means that if we have two complex numbers, maybe we want to call one of them z1, and it comes with an r1, and then a theta 1, right? And then z2 will come with r2 and theta 2. So we want to know how to multiply them. Well, let's see what happens if we multiply them. That is, multiply this here by that there. When we do and expand, FOIL, whatever you'd like to say, then this is what we're going to get. Clearly, the real part of z1 times z2 is going to be made of this first term, giant term if you want to call it a term, and then this last term, right? Because and multiplying I times r1 sine theta 1 with I times r2 sine theta 2, we get I squared, which is negative 1, and therefore the negative sign here. And then otherwise we get r1, r2, and then sine theta 1, sine theta 2, which is what I've got here. So this part doesn't have an I. This first part doesn't have an I. So we lump them together. We group them together to make the real part of z1 times z2. And then the imaginary part of z1 times z2 is made of this guy here, which has an I, and then this guy here, which has an I. Yeah? Okay, cool. And so doing the grouping as I just spoke of, we could write this here. Yeah? Okay, now we need to simplify this. In order to do so, we can use the sine and cosine angle addition formulas. We know that cosine of alpha plus beta for two angles alpha and beta is this here. Now, if you claim alpha to be theta 1 and then beta to be theta 2, you'll recognize that this here, right here, multiplying r1 and r2 in the real part, this here, is equal to cosine of theta 1 plus theta 2. And then if you, and the bridge, and then if you look at sine of alpha plus beta formula, then you'll reckon that this here is sine of theta 1 plus theta 2, all of this here, yeah? Okay, cool. So that's going to allow us to simplify the result for z1 times z2 tremendously. And we can simplify it in this way, right? And then we see that r1, r2 appears here and here. So we could factor it out. And we use our good old abbreviation for cosine theta plus I times sine theta as cis theta. And then write z1 times z2 a lot more succinctly as r1 times r2 cis theta 1 plus theta 2, where again cis here stands for cosine of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. So yes, basically you factor out r1 and r2 from the second to last step, and the remaining part is what I'm calling cis theta 1 plus theta 2, in case you didn't watch the intro video where we in detail explained what cis means and where it comes from and all that good stuff. All right. So where to from here? Well, I think what we said is we're going to give an example, but let's summarize this before we move on to the example. So in summary, given z1 is r1 cis theta 1, that is all of this if you want the longer version, and then z2 is r2 cis theta 2, or all of this if you want the longer version, we see that z1 times z2 is going to have to be r1 times r2 cis theta 1 plus theta 2. So this is actually a really neat discovery. One is in a way, you could argue that this is a good way to prove the sine and cosine angle addition formulas, this part. But the more important note is that multiplying by a complex number is actually a rotation by the angle that complex number comes with in polar form, right? So I'll dedicate a video to how multiplying by complex numbers amounts to rotations. So you can wait on that, but like just kind of as an appetizer, food for thought, right? As food for thought, like what this derivation shows is like basically like when you multiply two complex numbers in polar form, their moduli multiply, which is their r's multiply, and then their thetas add. But yeah, that's the result that what we've summarized here, and that's why like multiplying by a complex number amounts to a rotation by the angle that comes with that complex number in polar form. I hope you understood what I just said about rotation. If you didn't, then you could wait on the video where I'll in more detail talk about how multiplying by a complex number is the same as like a rotation, right? Okay, cool. All right, so here's a promised example. So let's take two complex numbers, z1 and z2 here. And first, like, let's just get our answer by multiplying them in rectangular form as they are. And so, you know, rectangular form, we do this and then like FOIL and stuff, right? Like, and so we get that FOIL or expand or whatever you want to say, and then simplify. And so that's a little bit like that. And things cancel, right? These guys here cancel, these middle two, and I times I is I squared, which is -1, and we have a -1 here. Coupling those, we see that z1 times z2 in this particular example should be -2. Wait, I didn't show that it's equal to -2 here. Wait, where did I skip a slide? Yes, I did. Whew. All right. I thought I like just accidentally forgot to put this slide, and I was going to be more upset. All right, so but yeah, like you can simplify here and see that you get z1 times z2 for these two z's is equal to -2. So let's do it in polar coordinates. So in polar coordinates, z1 changes to √2 cis pi over 4. You can plot z1 and see why it's got to be this in polar coordinates. It's pretty easy. Its modulus is the square root of the square of its real part plus the square of its imaginary part. So 1 squared plus 1 squared under the square root is √2. That's the modulus part. And then like this, if you plot it, would form like a 45-degree angle in the first quadrant. So clearly the argument theta is pi over 4. And this guy will have the same modulus, but will be in the second quadrant where theta will be 135 degrees or 3 pi over 4. But yeah, so the multiplication in polar coordinates is actually easier than the multiplication in rectangular coordinates, especially when you have lots of multiplication of complex numbers to do. But here, yeah, we said their moduli multiply and the arguments or the thetas add. So I just do pi over 4 plus 3 pi over 4 as the argument, and then √2 times √2 as the modulus. And this is why I'm claiming that it's easier to multiply in polar coordinates. And √2 times √2 is 2, and pi over 4 plus 3 pi over 4 is 4 pi over 4 pi. And so z1 times z2 is 2 cis pi. But remember, cis is an abbreviation. So if we get rid of the abbreviation and look at it the longer way, it's saying 2 times parentheses cosine pi plus I times sine pi. But when we distribute the 2, we get 2 cosine pi plus I times 2 sine pi. We know sine pi is 0 and cosine pi is -1. So as soon as we reckon that, we see that z1 times z2 gives us a consistent answer in polar coordinates. So we did it correct, yeah? All right, cool. I hope you enjoyed this video, and keep watching. Next video I'll make will be about de Moivre's theorem. So it's pretty cool, yeah? All right, and we'll do a pretty interesting hard question along with proving de Moivre's theorem in the next video. All right, I hope you enjoyed this, and keep watching. Take care. Bye.